Hi everyone, welcome to the fourth lecture in the course Computational Mathematics. With the today lecture we start a new subject that will span for a few lectures. Namely, we will concentrate on methods of solving univariate polynomial equations. Today's lecture will gather some basic information about roots of polynomials, of univariate polynomials, and I will also present closed form formulas for roots of polynomials of low degree. On the next few lectures, we will learn how to isolate and approximate the roots of polynomials, but today we begin with something more elementary and something which was done earlier in history of mathematics, which is, as I said, solving univariate polynomial equation of low degree using closed form formulas.
Before I give any particular methods for solving univariate equations, let me first gather some generalities concerning polynomials. I believe that you know all the results that will be presented in this section. Nevertheless, I want to show them explicitly so that you can refresh your memory on one hand, and on the other hand, we can have all these tools grouped together, so it's easier to refer to them later on when we need them. The first result that I wish to mention is called the fundamental theorem of algebra. It says that if we have a non-zero polynomial with coefficients in the field of complex numbers, then it has precisely DEC-F roots when we count the roots with multiplicities. So, in other words, if we have a polynomial of degree n, then when counted with multiplicities, this polynomial must have exactly n complex roots. This I believe to be well known. There are dozens of different proofs of this theorem, and I will skip the proof because it would take us too far afield here, and nevertheless we need to remember it. This will be most important on the next lecture when we will concentrate on the number of real roots. From this theorem, we have the upper bound for the number of complex roots and the number of real roots, which are much harder to bound, to estimate, to count, will be considered on the next lecture. Another of the standard result is so-called Witt formula. Witt formula says that we can express the coefficients of a polynomial using just sums of products of the roots of this polynomial. So the first version which I present here is for monic polynomials. So if we have a monic polynomial, so the leading coefficient is 1, then the sum of all the roots of this polynomial is minus fn minus 1. So this is minus this coefficient. Then the next coefficient, fn minus 2, is equal to the sum of products of every two roots. So this product is a sum of products psi I1, psi I2 for all I1 less than I2, and so on and so on. The coefficient fn minus k can be expressed as minus 1 to the kth power times the sum of products of k elements when the indices I1, I2, and so on, Ik, are strictly increasing. Finally, plus minus f0, so f0 times minus 1 to the nth power, is the sum of products of this form when the products are of length n. But since we have exactly n roots, due to the fundamental theorem of algebra, there are exactly n roots here, then there is only one product of this form which has length n, and this product consists of all the roots. So f0 times minus 1 to the nth power is just the product of the nth roots. This is a version of its formula for a monic polynomial when we had 1 here. If we have a non-monic polynomial, so if we have some non-zero polynomial with some non-trivial coefficient here, then we can reduce the problem of expressing the coefficients as using roots of polynomials, just dividing this polynomial, normalizing it, but just divide the polynomial by the leading coefficient. So we can go from this polynomial to the monic polynomial, dividing each coefficient by fn. Then we will have a monic polynomial, and we apply the Witt's formula for this monic polynomial. So the right hand side will not change, and the left hand sides will be altered in this way that every coefficient is divided by the leading coefficient. So if we have one version, then we have another version. I will present a very short proof of this monic version, and as we have seen, this final version, this general version, follows immediately from the monic version. And the proof for a monic version works like this. Since xi 1 up to xi n are all the roots, so we can write f in the following way. It's x minus xi 1 times x minus xi 2 times and so on x minus xi n. There is no coefficient in front of this product because we assumed that f is monic. And now we want to express this polynomial explicitly. We want to expand this product. We just multiply all these parentheses. So first we just take the x to the nth power. So from each parenthesis we just pick x. In each parenthesis we pick x, so we get x to the nth power. Now let us pick x from all the parentheses except a single one from which we pick xi I. So our next coefficient, next term will be x to the power n minus 1. So from n minus 1 parenthesis we picked x, and from the remaining one we picked xi. So if the remaining one was the first parenthesis, it is minus xi 1. If it was the second parenthesis, it is minus xi 2. And so on and so on. If it was the last parenthesis that we picked xi, then we have minus xi n. Now we pick x from all the parentheses except 2 from which we pick xi I and xi y and xi j. So we have x to the power n minus 2 times. And if we just pick xi from the first two parentheses, then it's minus xi 1 minus xi 2. But then the next one is minus xi 1 minus xi 3, and so on and so on. The final one is minus xi n minus 1 minus xi n. And so on and so on. We can keep picking the elements in a different order. The constant term is obtained if we pick the xi I from every parenthesis. So it is minus xi 1 times minus xi 2 times and so on minus xi n. So this equals x to the power n plus, in the next parenthesis we have minus 1 to the first power, minus 1 times a sum of psi I times x to the power n minus 1 plus, in the next parenthesis we have minus and minus, so minus 1 to the second power times the sum of the products psi I, psi j for I less than j times x to the power n minus 2. And so on and so on. Finally, the constant term is, we have n times minus 1, so it's minus 1 to the power n, times the product psi 1 times psi n. On the other hand, we know that the polynomial f has a form x to the n power times fn minus 1 x to the n minus 1 power plus fn minus 2 x to the power n minus 2 and so on, finally f0. Now the two polynomials are equal if and only if all the coefficients are equal. So this coefficient must equal this coefficient. This coefficient must equal this coefficient. And so on and so on, this one must equal this one. So what we get is that fn minus 1 is minus 1 times the sum of psi I for all I. Fn minus 2 is minus 1 square times the sum for I less than j xi, psi I, psi j, and so on and so on. The finally f0 is minus 1 to the power n times the product psi 1 and so on up to psi n, and this is exactly the Verts formula. So we have proved the Verts formula in case when f is monic. And as observed before, the general case follows immediately from the monic case. We have one immediate consequence of the Verts formula, namely this formula let us compute the arithmetic mean of the roots of the polynomial without knowing the actual roots. How we can get it? Let's look at the Verts formula here. Here we have a sum of all the roots. So the mean, the arithmetic mean is the fraction, the sum over the number of elements. So if we divide this by the number of elements, so we divide this sum by n, then we get the arithmetic mean. But this sum equals this expression. So if we take minus fn minus 1 and divide it by n fn, we got exactly the arithmetic mean of a polynomial. So we can compute the mean of the roots of a polynomial without knowing the roots. And this is very important. We say that a polynomial is depressed. It's depressed if the mean of polynomials is 0. So the polynomial is monic. This condition is less important. The real important condition is this one, that the mean of roots is 0. This means that the roots are centered at 0. In particular, since the mean of root is 0, using this formula we see that the mean of root is this fraction, and the fraction is 0. If the numerical is 0, then it follows that a polynomial, the monic polynomial, is depressed if this coefficient is 0 and this coefficient is 1. The leading coefficient must be 1 and the one before it must be 0 for a polynomial to be depressed. It turns out that we can actually depress any polynomial very easy, in a very easy way. We just shift the roots, shift the graph of a polynomial. we compose the polynomial with a shift that moves the mean of the roots to 0. So we replace any given polynomial f by a polynomial of this form, so that the roots of it will be shifted to 0. We will see the actual application of this on the next lecture, when we will talk about bounds of roots. You will observe that for a polynomial, for a depressed polynomial, we often obtain a better bound than for a general polynomial, because this fact that the roots are centered at 0 greatly improves the numerical computations associated to this polynomial, greatly improves the accuracy of the bounds for the roots of a polynomial. Now let me mention another fact concerning polynomials, which I believe you know. At least in Poland, this is taught at secondary school. This proposition says that if we have a polynomial whose coefficients are integers, then a rational number p over q can be a root of a polynomial only when the numerator divides the constant term and the denominator divides the leading term. Observe that we have only implication one side. So if this is a root, then this happens. Of course, not every rational number with the numerator dividing the constant term and the denominator dividing the leading term will be a root. It's obvious that there is no other application. But the only roots, if something is a root, then it must be of this form. The proof of this fact is very short and very easy. First of all, without loss of generality, we may assume that P and Q are relatively prime, so the greatest common divisor of the numerator and denominator is 1. So assume that the rational number P over Q is a root of a polynomial. So we have 0 equal f of P over Q. So let us expand the right hand side. So after expanding the right hand side, we have sum of this form, and we want to clear the denominator. So we multiply both sides by the highest power of q, which appears here, so by q to the power n. This way we obtain this equation, which depends on p and q. And if we look at all the terms except the first one, all these terms are divisible by p. Here we have p, here we have p, here we have p. So all the terms here are divisible by p. 0 is clearly divisible by p. So it follows that this term must be divisible by p. But for this term to be divisible by p, when q and p are relatively prime, the only possibility is that f0 is divisible by p. So because p and q are relatively prime, this is divisible by p, this is divisible by p, so f0 must be divisible by p. On the other hand, if we look at all these terms except the last one, so everywhere here we have q. So all these terms are divisible by q. So the whole sum is divisible by q. Clearly 0 is divisible by q. So it follows that the last term must be divisible by q as well. But again, p and q are relatively prime. So if fn times p to the nth power are divisible by q, p and q are relatively prime, it follows that fn is divisible by q. So we proved that both p divides f0 and q divides fn, and this proves the proposition. I have presented this proposition in the simpler way when we had a polynomial over the integers, but it holds in a more general setting with exactly the same proof without changing any single part of a proof. The same proof, the same proposition holds in the following setting. We have a unique factorization domain R, we have a field of fractions, then a polynomial with coefficients from a ring, from this ring R. If this polynomial has a root at some xi, an element, a fraction of the elements from this ring, then the numerator must divide the constant term and the denominator must divide the leading term. So exactly the same proves this more general theorem. Now the last of preliminary observations concerns the polynomial with real coefficients but complex roots. Namely, if we have a polynomial with coefficients in R and some complex number xi is a root of f, then its conjugate must be a root of f as well. So the complex non-real roots of f comes in pairs, in conjugate pairs. If xi is a root, then xi bar, the conjugate of xi, is a root as well. And again, the proof is very simple. So assume that f xi is 0 and expand the right hand side. So 0 is f0 plus f1 xi plus f2 xi squared and so on plus fn xi to the nth power. Now conjugate both sides. So we have conjugate here, we have conjugate here. But 0 is a real number, so if we conjugate 0, we get 0. And conjugate preserve sums and products, so we can express this way. So we can split it into a sum of conjugates. Now, as I said, conjugate preserve products, so we can split it even further to have it like this. But now all the fi's are real numbers, so fi conjugate is just fi, so we have this guy. And now when we look at the right hand side, this is just f of xi conjugate. So we have proved that xi conjugate is a root of f. Now we got to the second part of today's lecture, and I will present here some explicit formulas for roots of low degree polynomials. One of the problems that people kept asking from the very beginning of the algebra, from the very origins of the algebra, was how to find roots of polynomials. And of course, the closed form formulas are the ones that people dreamed of, the ones that people prefers because they are closed form. And so people ask, are there any closed form formula for roots of polynomials? And I will present such formulas for low degree polynomials. However, I must warn you that these formula are okay when we deal with exact numbers, when we have infinite precision, so when we express the root symbolically. On the other hand, if we work with floating point numbers, all these formula behave very bad. They are inherently bad conditioned. Don't use, so the bottom line is, don't use this formula with floating point numbers, but for exact numbers, for symbolic computation, they are okay. I will follow the historical path and will at the same time follow the path of increasing degrees of polynomial. First of all, let's look at the polynomial at degree 1. We have a polynomial of degree 1, so a linear one, and okay, this is trivial. as long as people were able to write this kind of expression, they were able to find a root of this expression. Just if this is 0, ax plus b is 0, when the root is minus b over a. So we don't know who was the first one to solve this, but it was the solution is known as long as the question is known. The second step is to consider quadratic polynomials. So polynomial of the form ax squared by b plus bx plus c. And here again we have explicit formula, and it is a formula that most of us learn at secondary school. It says that we compute the discriminant of this polynomial, b squared minus 4ac, and then the roots of a polynomial is 1 over 2a times minus b plus minus square root of the discriminant. This formula were already known in the antiquity in Mesopotamia, in Babylon. So there are archaeological proofs that Babylonians knew this formula. Of course, they didn't write it explicitly as a formula. They were expressing it as a way of doing things, a way of computing things, but hundreds of years before Christ, it was already known in Babylonia. To Europe, it was brought to Europe through the Arabic mathematicians, and probably the oldest European appearance of this formula was in 20th century in the Latin translation of the Savasorda treatise on measurements and calculation. I don't say it was published in Europe, because if you look here, it's 20th century, so it is before Gutenberg, before invention of printing. So it's hardly to say, we can hardly say that it was published. It was written. It was being written and rewritten by the monks. So there was handwriting rather than publishing that time, but it appeared in Europe in 20th century. So the next step was to solve the polynomial of degree 3. And the cubic equation were solved only in 16th century, so much later than the previous two cases. It was solved first by Scipion del Ferro in the early 16th century, but in a very special case when this cubic polynomial is depressed, when there is no term of x squared. There is no x squared in this equation, and the general solution was found by Tartaglia sometime later. Anyway, none of these two guys published ever their findings. The result was published for the first time by Geronimo Cardano in Artis Magna without actually crediting Tartaglia. Cardano learned the method from Tartaglia but didn't credit him in his book. And I will present you a method of solving a cubic equation which is very similar to the original work by Tartaglia. However, this method that I present here is due to Viette. It is slightly improved over the original method, but they are very similar to each other. So we are given a cubic equation. First of all, we get rid of this quadratic term by just depressing it. We know that this is the minus b over 3a is a mean of the roots of polynomial, so we substitute x minus b over 3a, and we get a depressed polynomial of this form. Of course, we can we can calculate p and q just doing this substitution. Now, what we want to do is to take to give an is to use another substitution. We instead, in place of x, we substitute y minus p over 3y. This way, if we substitute this thing in place of x here, we arrive at this rational expression, and we want to get rid of this y cube here, so we multiply both sides by y cube, so we get y to the 6th power times q times y cube minus p cube over 27, and in place of, instead of y cube, we write z. So we arrive at this expression, and if we look at it, this is just a quadratic polynomial in z. So since it is a quadratic polynomial, we can solve it. We can solve it using the standard way, standard methods, compute the discriminant, find the roots of this quadratic polynomial. So we have some root, we have two roots, but it's enough to take just one of it. We have some root zeta, but this is a root of this polynomial. So this is a solution in z. Now, when we have solution in z, we can trace back all this substitution that we had here. So we have zeta, this is z, this is solution for z. So to get a solution in y, we just compute the cubic root of zeta. Now we replace it here. We compute x, and so on and so on. Finally, the solution xi, the solution in x, is of this form, is this expression. So this is the Witt's method to solve the cubic equation. We can write all this substitution and all these steps. We can write them in a closed form formula, which is quite intimidating and complicated, but it looks like here. We can compute the one delta, the other delta. We can compute some constant c, and then when we have all these guys here, we can express the roots of f in this way, when zeta is the primitive root of unity of degree 3. So for those of you who prefers a short closed form formula, however much more complicated, here it is. So it is clear when our next step is to look at degree 4. Degree 4 was solved shortly after degree 3. Actually, it was done by a student of Cardano, Lodovico Ferrari, and it was published again by Cardano in the same Artis Magne book. I will not present the Ferrari solution, which is quite complicated. Instead, I will present a Lagrange solution, which is very ingenious and very smart and much easier than Ferrari solution, and uses a very fine idea at a certain moment. So let us again start with a quartic polynomial. And again, the first step is to get rid of this term. So by depressing the polynomial. So instead of 5 coefficients, we have only 3, p, q, and r. So we have a quartic depressed polynomial. And let us denote the roots of this quartic depressed polynomial by xi0, xi1, xi2, xi3. And we want to find these xi's. Of course, when we have disk size the roots of this polynomial, we can retrieve the roots of the original polynomials by shifting these roots again by the mean of the roots of this polynomial. So once we have this solution, we can solve this guy here as well. So the idea due to Lagrange was to take the following matrix and do a linear transformation of the roots of polynomial. So in place of these roots, he considered these roots. So we replace the roots xi0, xi1, xi2, xi3, which we don't know, we replace by another three unknown numbers, zeta 0, zeta 1, zeta 2, zeta 3. But the important thing is that if you look at the first line of a matrix, this consists only of ones. So if we multiply m by this vector of size, the first zeta, zeta 0, will be 1 times xi0, 1 times xi1, 1 times xi2, 1 times xi3. So it's just a sum of these xi's. So zeta 0 is the sum of xi's. But we know that the polynomial is depressed. So the sum of xi's is 0. We don't have a term x cubed here. So the sum of xi's is 0. So zeta 0 is 0. But what does it mean? It means that instead of looking for 4 unknowns, we are looking only for 3 unknowns. We a priori know zeta 0. We need only to find zeta 1, zeta 2, zeta 3. We don't need to find 4 unknowns. We need to find 3 unknowns. And how we can do that? We can construct a polynomial h such that the squares of these zeta 1, zeta 2, and zeta 3 are the roots of our h. So this polynomial is just obtained by multiplying x minus zeta 1 square times x minus zeta 2 square minus times x minus zeta 3 square. And if we multiply them, we obtain something like this. But now we will use the Vites formula. This is expressed in zetas. Zetas are expressed in xi's. So using Vites formula, we can express the coefficients of this polynomial h in terms of the xi's. Here I use the following notation that sigma k is the sum of I1 less than I2 less and so on less than Ik psi I1 up to psi Ik. So it's a product, it's a sum of products of length k. So in particular, so it is a sum of products of length k. And so here, so for example, here we have just a sum. Here we have sum, here we have sum, here we have sum, and so on and so on. Here, 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 everywhere here we have sums. And the sum of size, so sigma 1 is 0. So this guy cancels, this guy cancels, this guy cancels, this cancels, this cancels. This is 0, this is 0, this is 0, this is 0. So lots of terms here are cancelled due to the fact that we had a depressed polynomial. So this shortens to the following formula. If we just compute it, we have just minus q squared here, p squared minus 4r, 2p here, and nothing more. And this is a cubic equation. This is a cubic equation. If we just substitute here, this h0, h1, h2, we substitute to h. using this fact. For example, here we have just this guy, here we have just this guy and this guy, here we have just these guys. So these are exactly these terms. So this is a cubic equation. And since this is a cubic equation, we can solve it. We can use the methods for solving cubic equation that I presented a few minutes ago. And we can find the zetas, zeta 1, zeta 2, zeta 3. In fact, we will find zeta 1 square, zeta 2 square, and zeta 3 square because these are the roots of h. And then we take the square roots of them to get zetas. And now when we have zetas, we can multiply the zetas, the vector of zetas. Here is 0 because the polynomial was depressed. Here are the 3 zetas that we just computed. And we multiply it by the inverse of m. Actually, the m has such a special form that you can check it by yourself that it is self-inverse. So the inverse of m is m again. So instead of m inverse, we can just write m, and we multiply the zetas by m, and we get xi's, which are the roots of our f. So this is a way of solving solving polynomial equation of degree 4. Of course, one can ask whether it is possible to solve the polynomial equation of higher degree, of degree 5 and above. And the solution to that was found first by Ruffini, but his proof had some serious gap, and it was improved by Aber sometime later. And I will express it, but in order to present Aber-Ruffini theorem, I need to introduce a notion of radicals. The definition is may look quite complicated, may look quite intimidating, but it says that, okay, some element alpha is expressible in radicals over a ring R if we can get from the ring R in a finite number of steps such that alpha will be here in the last ring, and each of these rings are constructed from the previous ring by just appending the nth roots of some ai. So we append to ri minus 1 nth root of ai to get another one. Okay, this may look complicated, but in short, in a nutshell, this says that element alpha is expressible in radicals if it can be written as a finite formula which contains plus, minus, times, divide, and a root of degree n, nothing else. So, for example, something like, okay, the cubic root of 1 minus 2 over 3 plus the square root of 5 plus, let's say, the square root of 7 times the 9 times 9 root of 1 plus 3 over, let's say, 4 is expressible in radicals. Because here in this formula we have only finitely many sums, divisions, sums, products, differences, and divisions, and roots of any degree. So if we can write something like this, finitely many operations, plus, minus, times, divide, and compute the root of degree n, then it means it is expressible in radicals. And the Aber-Ruffini theorem says that if we fix a degree n 5 or above, then there is always a polynomial of this degree such that it has roots, but these roots are not expressible in radicals over the coefficients. So in short, it says that, okay, starting from degree 5, there are polynomials that have roots, but you cannot write these roots in a finite form. You cannot write this root in as a finite expression that involves only the four arithmetic operation and roots of any degree. In particular, this means that you will not find a closed formula for roots of polynomials of degree 5 or above.
That's all for today. Thank you very much for your attention. As you see from the Abel-Ruffini theorem, for higher degree polynomials, our basic approach of using closed form formulas will not work. So on the next few lectures, we will develop other methods of solving univariate polynomials which are maybe not so straightforward, but contrary to the closed form formulas, those methods that we will develop actually works and provides us with roots of polynomials, with roots of univariate polynomials, with any desired accuracy. So I invite you for the next lecture in 2 weeks. See you in 2 weeks.